I'm kind of going to like the base.
Yeah, so.
Just so we're on the same page.
Yeah, so just if you think it's going too slow or too fast, let us know. Or if you don't want to speak up in person and you think it later, just shoot me an email and be like, that was way too fast, or that was way too slow, we should be more advanced or less advanced or whatever. Cool. I also think if whoever's running the presentation for the week is okay with it, we're going to record them and maybe put them on like a YouTube channel or something. So if you didn't make them, they'll be there.
Yeah, but this is what the recording would look like, right?
Yeah, it's not super high quality. Maybe we should have brought like a little
There's,
pad or
reflection.
something.
Yeah, so maybe we'll advance and
We'll
start
only
making
advance.
profits on our neat shirts.
Yeah. You know, on our ad revenue.
Yeah.
Cool.
Okay, cool. So here's the first thing. So as you probably know, we're going to talk about linear algebra. And what about this? I'll say it, but just think to yourself, like, why is this linear algebra and not like quadratic algebra or cubic algebra, right? It's quite specific that like each thing here is only to a first exponent, right? So it's lines, we're talking about lines, or, you know, systems of equations that you could represent as a series of lines. So like linear algebra comes up a lot in like ordinary differential equations and other things where we're going to solve these complex systems, but you can break them down into like a series of lines. And then like the sum of the parts actually does equal the whole. So that's kind of a unique special property. So for this guy here, little guys, they look like primes, they are not, they are just themselves. Also with this equation, how many unknowns do we have to solve for? Yeah, two unknowns. Two unknowns. And how many unique equations do we actually have to solve them?
So two.
Nope. Unique equations. So what this one is actually is just that bottom one times 2. So this is the exact same information. So you cannot solve this to get a single answer for X and Y. So this matrix, right, has a problem in that we have two unknowns, but we only have one unique equation. And so this is just kind of the rule of linear algebra and the rule of solving. If you want specifically to get a point estimate for X and Y, you need as many unique equations as you have unknowns. And that's just always true and something I frequently go back to. So that's our first issue with this little guy. So we can see that if we were to even try to solve it, right, all this like would cancel, right? If I tried to multiply this by a -2 and do our normal algebra to like kill one of these variables on the way, I would kill everything. And so we get out something true, right? That like 0 would equal 0, but that's not helpful at all in terms of like solving for X and Y. So you always need as many equations as you have unknowns. So that's thing to remember, number 1. Great. And so let's just take a little more generic guy. And we'll do mostly, I think all my examples are 2x2 matrices just because they're the easiest. And then when we get to, we could do 3x3, but I don't think it's really critical for this group because like beyond understanding like this basic concept of how you do it, then you would just use like MATLAB or something else for like real matrices in your data. Like it's more important that you then focus on like real algorithms that solve real big problems. Toy problems on the board we can keep small. So, okay, so how are we going to represent this as a matrix and some vectors? Well, we have an X and a Y in each one. So we're going to turn him into a vector. We'll just call him like an X with this little hook on the top. And so typically we always do vectors in lowercase and matrices in uppercase. And so we can just call this guy of A, B, C, D, the A, and then this little vector of EF values. We'll just say equals V. And so usually it's just extra effort to write these, but it's implied when you see these kinds of things that like these are vectors. And sometimes maybe they'll be italics or like bolded, something when you're typing that distinguishes it, but just writing, you can throw that on. And so how did we get here? So let's see, can you see the board? Fine. All right. So to get this back, I'll do a little like matrix algebra up here of like multiplying a matrix times a vector. So the way I always think about it is like, since we saw where it came from, right? I just think of like picking up this block and laying it down on it. And that's how I visually do them. And so what's happening is we pick up this block, lay it down on there, they get multiplied, and we add it together. Because what we have here is a 2 by 2 matrix, and we have a 2 by 1 vector. Right, so these are row by column and row by column. And so this has to match in the middle in order to get that actually to like line up and lay down. And then our answer is going to be whatever's left on the outside. So our answer will be a 2 by 1 because that's what remains here is a 2 by 1, right? And so there is this concept, right, in linear algebra of like left and right multiplication or things happening on the left side or the right side, because we could swap these and I could try to do this matrix times our vector, but now they don't line up. So that multiplication is not going to work. And let me know if I'm going too fast or you have questions. But so yes, picking this up, dropping it, we kind of get the exact same thing back out. B1, and so it adds together. So that's like one thing, right? And that one thing it equals is E. And then their next CX plus TY, right? And that equals F. And it turns into one thing because we added it together. And so that would be true for any size of this system, right? We could always take our variables and if they're matching, right, and pull them out. Make sense so far? Sound good? Okay, great. So yeah, that's how we multiply. Keep this in mind. I'm going to erase the board. Let's move on. So let's go back to our parent equation. And I'm going to drop the variable names. What would be, if these were just numbers, right? Let's maybe say like 1/2. Or I'll give them a new name. Z equals T. And these are just little coefficient numbers. What would we multiply by to get rid of this 1/2? 2, right? We have some concept in normal math of not so like an inverse, but something that's going to like do and undo a number. For everything we have a pair that would undo it, right? And if we wanted to like make that would be a 1, right? And so it's the same thing here, where we have this concept of an inverse that will make everything inside that matrix 1, and then when we multiply by our vector, we just get that vector back. And so when we multiply by an inverse, this guy will turn into a big I for identity. That's our identity matrix, and it looks like just ones on the diagonal with zeros everywhere on the off diagonal. So identity matrix. And so the same thing is true for, like I was talking about, left and right multiplication. To be the inverse of A properly, you need to be both a left and right inverse. So that's something you can check and double make sure. And then I'll go into some little ways in which we calculate inverses. But for a 2 by 2, it's quite easy. And then it gets a little bit more complicated. And we'll do a kind of like the long original kind of Gaussian elimination process by which we'll solve for an inverse. But that's quite slow and tedious. And you would not do that on like a 1,000,000 by 1,000,000 matrix, right? You're not going to use that to figure out what is the most searched best page if somebody like types in cats on Google, right? They're not doing this to solve and page rank for you. They have way faster algorithms. So inverse, you must be left and right inverse. And I think that's an important concept. It all comes back to, do my sides line up? Let's do an actual example. I think this is a new example. So we've got our matrix. So this is the x and the y, right? So x times y makes this guy, and then summing together equals this. So this is like our function, and this is the output, right? So x and y are like the inputs to the function, and this is where the answer is, right? So we have like, you only have $4, but you want to get like apples and oranges, right? How much can you get with your $4, right? We break this down. So what we're going to do now is called Gaussian elimination. And I don't know, who here has like ever taken linear algebra? Okay, cool. So you've definitely done this, probably the very first time you ever took it, and maybe you just don't remember. So we'll do it again, just because I feel like, why break something that isn't broken, or try to fix something that isn't broken. And so the goal for Gaussian elimination is going to be to take this matrix and turn it into the identity matrix. And then by the time it's just an identity, we'll have this whole guy turns into an identity. And then our answer will be some A inverse B. And one way that you could also code this, if you don't really care about like this solution, but you actually really just want the inverse, you can just put an identity matrix on the other side, and it'll keep track of all the things we've done. And so the only things that are allowed to do are, we can take linear combinations of things here and multiplying them by constants, adding and subtracting them, and use that to eliminate these and start turning them into ones and zeros. Okay, so we're going to go ahead and do that, and maybe it'll become more obvious as I keep moving through. So let's do the first one. Okay, so the row order, not nearly as important as the column order by which you do this, because, right, we want to turn this into a 1 and a 0. So as we move through, if we're trying to do it like this one and then this one, then every time we go to like add and do something again, we're going to add in new information, we're going to mess up what we had just put all this effort into. So you need to go in column order to solve this system with this type of algorithm. So let's do the first one. So we can kind of see that 6 here is 2 times 3. So if I use this 3, I could multiply by 2 and subtract it. And so what we do to one side or one equation, right, we have to do to everything. It's not at an individual level because it's still math. We're not changing the equation, we're just changing how it looks. So whatever we do to one thing, we have to do to everything, and it will just shift it. Let's do that. So I'm going to choose R2 minus 2R1, and that's my first thing there. So let's kind of, I always am a scratch paper person. So let's write that down. 6, 4 minus 8 minus 2, we get a minus 6. We get a positive 4, right? Negative 2 times negative 2. And then 4 times negative 2, also a minus 8. So we get 0, 8, minus 16. And so all I did is this is now our new row 2. Nothing else has changed. This is tedious and somewhat boring.
Wait, can you repeat what we did?
Fix that. So the rule of this, so the goal of this game, right, is I want to turn this matrix into an identity matrix. So my goal is to turn these off diagonals into zeros and the on diagonals to ones. And so you're allowed to multiply by whatever you want, right? So multiplying by a constant, that doesn't change this equation, just like, let's maybe say like x plus y equals z. It would be equally true that like 5x plus 5y equals 5, right? So you're allowed to do that, multiply by a constant. You're also allowed to use these other rows to start eliminating things, because just multiplying by a constant, the only way we're going to be able to like kill something is if we multiply by 0, and that's not helpful because we want to just kill one thing, not everything. While it's true that 0 equals 0, that's not helpful in solving our puzzle. So you're allowed to use the other rows here to do linear combinations. And the first one I picked was to take this 6, right, and use 2 times this first row and subtract it. So this is row 2 times 2 of the first row, 2 times the first row. Row 1. Here's row 1 times 2. That's this. And then we're combining each column. And so by doing that, we've done 1/4 of the puzzle. We've gotten a 0 here. And I chose it in this order because it gets quite annoying when you try to go for this one first. Like this is a 3. So we could have multiplied by 1/3 and we would have gotten our 1 for very cheap. But now we have to keep track of a -2/3 and a 4/3 for the rest of the time solving. So it would be best if you tried to just keep things integers if you're doing it by hand. But we will get some fractions unavoidably because now we still need to do that action. We still have to divide by 3. We just kind of got one integer addition. So yeah, that's the next guy. R1, so times 1/3. And if we were doing it up here, right, we would be breaking down our guy. So I've done that as well. So maybe I'll just keep him up there in addition. So I'm just going to keep track of here of the things we did, but you'll see in the end. So this guy solving the equation we originally laid out, this guy finding the inverse. And we're just maximizing space in the board. Okay, so if we do this, we're just taking this new, right? It's not really new, nothing changed. Row 1 and multiplying by a third. I'm going to bring him down here. So we get our 1 minus 2 over 3 and 4 over 3. And we need to keep our new row. So that was that step. So we make undergrads do this for a while because they don't know how to program. And this is, they have to do it by hand. But, you know, by the time you take a like algebra lab and use like MATLAB, this will happen for you very quickly. So MATLAB, fun fact, originally designed by someone teaching linear algebra at Stanford. And that's why that thing doesn't index from 0, because it's created by a mathematician and not a computer scientist. What did we learn?
So why didn't you do anything with the bottom row for this? Like,
Yeah, we could have done multiple steps. We could have also done maybe like R2 times an eighth, which is our next step. But what's happening here, right, is we're just doing each thing to each row. So I'm going turn by turn, trying to get one piece of the puzzle. So step 1, I turned this into a 0. Then I was able to turn this into a 1. Next thing is to start looking at how can I turn, what's the next easiest thing to turn? And here, multiplying by a constant to turn it into a 1 will be the next easiest thing.
so you don't have to do for each row, you can just like do the R for like one row. But do the-
Yeah, exactly. Like this very first one, you'll see by the time, in order to turn this guy into a 0, I'm gonna have to use the other row to do that. Because the only way to keep this a 1 and only change this one, it's gonna have to be some combination. And so the benefit of like working in this direction is now I've turned this into a 0. So anything I hit it with will stay 0. And I'll be able to keep my 1 and not accidentally introduce some new noise and then like mess up my steps. So that's why we move column by column. Within a column, which row you choose is really just dependent on whatever's easiest. Make sense? So yeah, we could do that here as well, 1/8. So what do we end up with? We end up 1. Slightly less, slightly more space efficient. Okie dokie. So yeah, we just did that. So now it's the very last thing. The very last thing to kill is this minus 2/3. So we're going to use row 2 to help us do that. So what's the only thing we should multiply row 2 by?
2/3.
Positive 2/3, right? Because he's already negative. So we don't need to subtract anything like we did above. So we're just going to add 2/3 of this row to that one, and it will kill it. So I'm going to write that here as we have R2 plus 2/3 R1. That's the action. I haven't been recording it here, but I'll write the solution up in a second. So we could do our scratch paper. So let's see, we have R2, which is now 1 or 0, 1, -2 times 2/3 R1. So we've got, this is correct. Yes. R1, I have opposite. Ta-da. It's like, that's not working. I could tell, because I was like, there's no way I'm adding something to the 0. All right, so R2, so 0. Nope, I wrote this wrong. I'm reading what I wrote correctly. There we go. Okay, so R1, 1 minus 2/3, 4/3. And now we'll multiply through by 2/3. And so the 0 stays 0 when we multiply. Right, this does turn into a positive 2/3. And this guy, 4/3. -2. Right, so it's our -2 times 2/3. So that's just a -4/3. So we happen to get lucky and just get them to cancel. We don't actually have to do. And so our answer here for this equation, right, if you were like thinking apples and oranges and these are the price points, right? You could get 0 apples and you could 2 oranges. So not really a helpful integer example, but for something else, maybe like where do these two lines intersect, right? They intersect at 0, -2. Yes, exactly. They're too expensive, so save up. So yeah, this just happened to turn into a 0. That was not our goal. And then up here, I will write down what that guy is supposed to be after the end. And so, after we turn this into the identity matrix on this side, which is basically what we just did, right? We could have been recording the same thing on the other side rather than trying to solve this problem. And we would have gotten 6, 1/12, -1/4, 1/8. So a lot of work to get the inverse of a 2x2 matrix, but we did it successfully.
Right side, like the 1/6, 1/12.
Yeah, this guy I got from doing the exact same Gaussian elimination process. But what I did, instead of keeping my answer there, I wrote it as 3 - 2, 6, 4, 1, 0, 0, 1. And so it's the exact same thing we did going through. And so you'll see as you fill it in, it's like recording the kind of steps we did. You'll see the linear combinations. And in the end, this turns into A inverse, where this matrix is A. So we'll get the inverse on the other side. Fast, but we're gonna do now. Yeah, we're gonna do a cheap and fast way to get A inverse for 2x2. Gaussian elimination, which is kind of one of the most introductory, like, do you understand we can add and combine these rows? Because it's still just algebra. It's just algebra of lines. Okay. Okay, cool. So I'm going to erase now. Let's maybe keep that one there. That is A. That's what we care about. So here's A. And so in order to get this guy A inverse, we just did this uncomplicated thing. But we could also do something cheap and fast. And so let me write this maybe as like CD initially. And so there is a rule in which you can do it, and I won't really go into why this rule is what it is, but we'll see that we get out the same thing. And so our rule is to get this A, and to get A inverse, you can do swap these two and then negate these two. So D A minus B minus C. And then you have to do one more thing, which is multiply by 1 over the determinant of A. And I'm going to talk about the determinant right now. And another way you've seen this is like A straight lines. So these straight bars next to it, like a absolute value of the matrix, is not what that means. It's saying take the determinant. And so the determinant is a really special, useful like tool for just understanding things about our matrices, because the fact that this inverse exists, right, is highly dependent on this determinant existing and being non-zero. Because as soon as I do 1 divided by 0, what is that? Sure, infinity though. Yeah, it's gonna blow up to positive infinity. Right? Yeah, so it will blow up is the mathematical term for that actually. So yeah, this blows up the whole thing. So determinant being a non-zero, right? Helpful. And that means A inverse actually exists. And why wouldn't A inverse exist? We could even just look back at our original guy, or maybe let me just put something cheap here. All right, like this is, I haven't even tried to pretend like this is two unique equations, but we could. All right, let me make this like a 2 and make this a 4, right? How many unknowns is this? How many unknowns? 2. 2 unknowns. How many unique equations? 1. Only 1. You can't solve this. You're not going to be able to invert it, because as soon as you do, right, let's take this, right, the determinant here, I'll show. I actually showed that one. Okay, it's actually just A times D, our diagonal, minus B times C, our off diagonal. That's the determinant of a 2 by 2. And basically, like all the bigger matrices, some of the like means by which they calculate their determinants really do break down to like this thing times a 2 by 2 matrix that you'll get the determinant of. So this is critical knowledge. Yeah, AD minus BC. So that would be 4 minus 4 to 0. And that tells us we have a linear dependency. You do not have enough information encoded in your matrix to solve. So this right here, no answer, right? That doesn't exist. You're not going to find the X here, right? And that was your goal. So without that, you're not going to find X. And so as well, we've kind of just been using square matrices, but you know, it's also true that the determinant won't exist for non-square matrices. Because it's the exact same concept. You have either too much information or you don't have enough to solve your problem. So this is a 3 by 2. All right, so you kind of see I have like the identity matrix here with an extra row. So how many unknowns are here? 2. There's 2 columns. Each column is an unknown variable. How many pieces of information do I have? 3. So by definition, one of these is redundant, because I only need as many equations as I have unknowns, right? And so that's why determinants and things, they're happening on square matrices, because this is a perfect pairing of unique equations to the number of unknowns, and that is why it is square. If this is redundant, right? So one of these could go, right? And same if we try to do the opposite. Now I have a 2 by 3 matrix. And how many variables do I have? 3. Number of columns. I have 3 variables, but I only have 2 equations. So at no point are you going to solve for x, y, and z. You do not have enough information, even if these are unique. It's just not enough. So there's no getting determinants of that. Okay? So that's an important concept there. Of course, you can have non-square matrices and use them. Like a common one would be like ranking like sports teams that have played against each other, you know, given that they played like some uneven, like each row is like a game, right? Each row is a game, but you only have so many sports teams. Like all that is true information. It's just like we're going to do different things and ask different questions and like what is the determinant of that matrix, right? So non-square matrices certainly exist in the wild, but if you want to get the determinant, you're going to have to do some other things, right? And even like here, this would be like A, and this would actually be its transpose, where I take it and I just switch it. I just pick up these blocks and I lay them down, pick them up, lay them down. That's all that happens. So this is the transpose of that matrix, and it is always true that you can multiply a transpose, a matrix by its own transpose, because, you know, its insides are always going to match. Even if I put this over here and did that kind of multiplication, right, the 3 and the 3 will always match. So you can create square matrices from your non-square matrices, but at the end of the day, you need to remember what you multiplied by. But so far, that was pretty quick. But the transpose is not a crazy concept. It's literally just shifting it. You've probably even done this in Excel. I take my my headers and make them column labels. What to do? I'm going well. So I'm going to. Let's go back to our problem with Gaussian eliminated and just get its inverse. Okay, so here's my little guy. So let's do our determinant first. So that's A. So the determinant of A, you might see written. It is these guys, this on diagonal, 12, so 3 times 4, minus is built into the equation, a minus 12, right? So, minus 24, so that's our determinant. And so that's going to go out front, 1 over negative 24. And then we just need to do our swap and negate.
It's just ready.
Got it. Awesome. Good job. Good catch. Yes, positive, positive. Okay, so let's do these. We're going to swap these on diagonal, negate the on diagonal. So let's do that. 4 here, a positive 2, a minus 6, and a 3. 1 over 24. And so hopefully we get out what we said we were going to get. But I'm pretty sure we do. So yeah, how many times is 4? Go to 24, 6 times 2, 12. Minus 6 goes into 24 4 times. It stays minus. 3 goes into 8 times. So much cheaper for a 2 by 2. Obviously, if you try to get determinants and other things of bigger and bigger matrices, like there are much cheaper ways to do it. If we have enough time, I'll mention one. But this is kind of basic. Your determinant is really useful even when we start getting to like ODEs and making the matrix representation of them and trying to find different like things about them. So determinant stays pretty useful. Okay. So I'm going to erase this and maybe just mention we discussed transpose. So we're on to trace. Trace is incredibly easy, but does actually come up in some things, so you might want to remember it. So little TR of A equals, so that guy means trace, is the trace of A, and it's actually just the sum of the diagonal elements for an n by n matrix. So n by n square matrix. And so this is just the sum. So little I, we're going to talk about how do we call this is the typical notation where your first index says my row. A is a row, comma, call. And it tells you your location in the matrix, which is quite helpful when you're going to actually like code these things up and program them. Like you should and how you could use nested for loops to do all your things, right? And it will, for I, take you on your first row, and then J move through your columns, right? And so for little things, nesting for loops, not so crazy, it happens. But the bigger and bigger it gets, right? You're gonna not want to have to touch every single thing every time, right? So keep that in mind. So, but trace is cool. I was kind of looking it up last night, like how do people use it? And it actually does kind of come up in a lot of machine learning problems in terms of like ranking the complexity of a problem or a matrix in which you're about to work on, which I think makes sense. And so all it is just summing up our diagonals. And so even in ODEs, like we use this a lot, the trace of a matrix plus its determinant, you can get like this nice map of like what kind of solutions you're expecting. Like, do you expect 2 real solutions, 2 imaginary solutions, things like that. So that's in the Stephen Strogat's ordinary nonlinear dynamics and chaos, ordinary differential equations book. Really good. Highly recommend. Okay, great. We have just enough time to mention the last thing, which is, I think, more useful probably to this department and people. And so this next thing called LU decomposition. So LU decomposition is pretty much exactly, it reads quite well. This is a well-named thing. So L means lower triangular matrix, and this is an upper triangular matrix. And they do look like triangles. So here, right, we could have L1, maybe do lowercase. And then 0. So there is a lower triangle here of non-zero values. Some of them could be 0, but the point is that it's non-zero. And then the upper triangle is the exact opposite, right? Where we have values in the up and only a 0 there. And
Do those include diagonals of triangles?
maybe not.
I don't know.
Yeah, I'm trying to remember because what I wrote down was just more of the like symbology. of it, but we could certainly do one. Because I want to just mention this and then LUP composition, which is essentially the same thing. They might be on the diagonals or not. I can't remember. But they are. Okay, yeah. So thank you. Good. So yes, on the diagonal, this is correct. And so what is the benefit of this is that when we can, if we could take A, and so the whole point is that we're going to take our matrix A, and let's say A is completely full. There are no zeros, right? Which means as we go to do computations, we're not getting any cheap storage. We're not like just killing numbers and getting zeros. But if we could break it into this L and U, we've generated a huge chunk of zeros. And so like getting the determinant of this gonna be cheap, right? Whereas maybe just getting the determinant of A alone is gonna be very expensive. And the cost to just break it up much cheaper. So this also comes up if you have a matrix that's just simply too large to store in like your computer's working memory, right? Like we have like a cache, right? And that's where we can keep things in the back. And then we have the like upfront things loaded onto our computer. And it's going to have to come to the cache, get things and bring them to compute, move back and forth, right? And so if you can't even store this matrix in your working memory on your computer, it's not gonna load and it will cry at you. But if you can store this guy, right, you could easily get the determinant of this and then the determinant of this and then come back. And I wasn't really gonna discuss this, but I'll just mention like why can you store this one easier? Because same with our IJ, right, that I said is how we call this like II, right? So for like 1, 1, I have the value L11. And so I could actually just store vectors that are the location of this and the non-zero value there. Because there's not really a huge point to storing so many zeros when you know they're just going to kill things. So sparse matrix algebra is very cool and very helpful. And it really comes down to like, let's not try to store this entire matrix. Let's just store our non-zero elements. And we know that the other things are zeros. So even like R, MATLAB, really powerful sparse linear algebra. But even in addition to this LU decomposition, so actually let me write something out really quick, just so we can see what I'm talking about. So if A equals LU, then in our same problem from before, right, I would have LU in our little X vector equals B, the answers we want. And the way we're going to do our algebra, right, we need to hit these with its inverse to kill it on that side, right, and keep going through like this. So U X would be equal to L inverse B. Same for the next guy. And so we'll end up with just X equals U inverse L inverse B. And so these will be much easier to get the inverse of than a really massive A. And so not only because we need the determinant in the inverse like we calculated earlier, but like these are still going to be triangular when we switch them. So that's quite helpful for even trying to do this multiplication first, right? And then what comes out of that is a vector, and then do that multiplication. Even that's cheaper, much cheaper. So very helpful. And so kind of from the very first problem I did, where I used like the second row first to like mutate the first one. You can do this thing called LUP decomposition, where instead I just have some permutation matrix A. And what it's going to do is swap A around so that it's actually in the optimal order to then do these matrix computations. So not always critical, especially for little things like this. Like we could have certainly swapped these rows and then I would have hit the 1 and then done the 0. But for really big matrices, swaps are like incredibly cheap. They take very minimal time. So if you could swap and orient your matrix in the best way possible, then decompose it, then you can do much cheaper algebra on a really big matrix. So I think that was more or less, oh, and then just that. Back to just one more determinant fact before we go. Right, the determinant of P. Determinant would be equal to the determinant of L times the determinant of U. And that might seem very simple, but there are certain like actions to matrices which do not like preserve these kind of normal math laws we have. So it is important to check and make sure that like the action you want to do, and honestly the actions we use most frequently, preserve these, and that's why we like them and use them, because it's not going to be helpful to decompose this if I can't get out the determinant of U and the determinant of A and bring it back together to only get the determinant of A, right? That's a different problem. So this is helpful. And here P, since P is a permutation matrix, it's really just like our identity matrix. Like let's maybe put that guy there. Zeros everywhere else. Pretend these are big zeros. Right. There's multiple. So all I've done is done row swaps. So the determinant of an identity matrix will always be 1, but every time you swap a row, you hit it with a negative sign because you've now changed, right, in that subtraction. So our determinant of P is actually equal 1, -1 to the n. Right, and this is true even for a tiny matrix, right? Let's.
What is n here?
And it's just the number of the size of the matrix. That looks not square, but I intended it to.
So if you have an identity matrix,
And swap one row.
and swap one row.
Well, like so this is just this is P itself. This is not the identity matrix.
No, but we can the identity matrix.
Yeah, it can.
So in that case, the determinant of identity matrix is 1.
So you did no permutations?
So I'm saying is like
Maybe just minus one then?
about -1.
Mm.
The identity matrix is a permutation matrix which does nothing, and it should not depend on anything.
Let's just maybe do one. So maybe n is the number of swaps then.
Yeah, the number of swaps could be, yeah.
That's right, that is a K. Yes, so K, number of swaps. So let's just do one here, like 0, 1, 0. Right, the determinant of this would be 1. And then if we swap it, right, now we have 0, 1, 1, 0. We have 0, minus 1. Right, we've changed the order in which we've taken things. So now the determinant is -1. So for every number of swaps you're doing, you're kind of doing and undoing the sign here. And that's just true of all the matrices. Making swaps changes the sign of your determinant. Okay, I think that was more or less all I wanted to talk about. I think we're pretty much it. Exactly time. Yay. I don't know how well this recorded. Yeah.
Stop recording. If you'll have any questions, you can call us back.
Yeah. I'm trying to hit